Aspetta, provo a togliermi da qua perché non mi riesce.
Sì, sì, a questo punto non serve più. Qua c'è un super.
Sì, sì, questo è esattamente il PowerPoint. Però io ho messo di scarica, ho messo in download. No? C'è sempre uno stress, però poi. Allora, fai, salva, gli dico presentazione, metto in PDF. Errore durante l'esportazione di possibile connessione al servizio online.
Ah, perché lo sono online. Proviamo a ascoltare solo. Proviamo a copiare il PPT. Ma quindi ci sarà un lettore di PPT. Qui c'è PowerPoint, quindi puoi anche.
Allora te lo do
Qui
in
c'è il
PowerPoint.
PowerPoint.
Te lo do in PowerPoint. Mi secca sempre un po', che poi la gente ci può.
No, ma io adesso poi ti faccio il PDF, non carichiamo il PowerPoint. Quindi,
Vabbè, sì, scusa.
non va neanche. Dopo uno lo prende, lo modifica, cambia il nome. Vai che anche col PDF. Grandino, Verso gli studenti ancora non ci sono i tutti.
Costano 0 mai di come se non gli piace scaricare.
Non mi piace la chiavetta? Non vede bene la chiavetta? Dobbiamo provarne un'altra?
Se no, senti, andiamo direttamente da qua e via, perché
Abbiamo
quello te lo mando dopo.
no, ma registrare per la lezione.
Alla lezione, ok? E niente, su questa chiavetta non ci riesco.
Hai un su Google Drive?
No, perché lui non è.
Adesso lo stiamo
Tu la chiavetta non ce l'hai, la chiavetta.
Avevi visto era un problema perché aveva detto SD disk.
Sì, sì, quello che avevo tolto.
Adesso sei illuminato. Vediamo se mi piace.
Allora esco da quella qua.
Devo decidere cosa staccare.
C'è spazio qua, Gabriele.
Ah, c'è.
Ma vuoi fare te con Windows 5? Poi fai le funzionalità, basta integrarlo. Anche di gestione di risorse. Si chiamava però. Vabbè,
Vecchio.
Vedi anche il fatto.
allora,
Adesso lo copio. Poi dopo
la carichiamo anche su Indico direttamente.
allora dobbiamo fare PDF prima.
Cos'è invece questo?
PPT. E tutte le slide esportiamo?
Spero che ci siano.
No, no, nel senso che magari dei backup che vuoi tenerti per te.
Ah no, non ti preoccupare.
Sono 60 gradi. L'italiano è
Qual numero? Carichiamo già, Marco?
Sì.
Casomai tu mi dai dopo 40 minuti. Sì,
Bisogna
perché
accedere con
tanto
un
poi
account
io
forte.
parto.
Io non so se io può
Allora
caricare.
carico io, se stacchi la chiavetta.
Allora,
Questo faccio anche l'andata avanti e indietro da là.
Sì, se è stato messo il
No, ma io adesso ti faccio partire direttamente questo.
Tu hai il pointer, ma tu già.
No, questo è quello. No, non è il mio.
Dopo mi togli questa.
Diciamo che si può sempre togliere.
Vado.
Perché sono dei byte. Prima non andava. Ma quello era già attaccato lì?
No, attaccato adesso.
Ah, va.
Proviamo. Vai su presentazione. Hai già fatto partire la registrazione.
Guarda.
Sì.
Vediamo che quando.
Prova a cambiare.
Non lo vede? No, aspetta, forse non è.
Ecco, prova adesso. Ok, perfetto.
Sì, va bene. Vabbè, ok.
Andiamo indietro?
Aspetta, vai all'inizio. Ah, glielo vai all'inizio perché sennò non ci vado io. Boh. Ok.
Good morning. So we are going to start. Sorry for this delay. So now we change somehow topic with respect to the previous lectures. We are on Axions, okay? Axion phenomenology and also experimental networks. The lecturer is Gianni Carugno, better, much better, and he's from INFN Padova. As for the other lectures, you have 1 minute to present yourself without any information before.
Okay. So,
as for the others.
Okay. So, good morning. First of all, I'm an experimental physicist. I like to develop new instruments and try to connect new instruments with fundamental physics. So I move on. I was the first one doing liquid xenon TPC and making physics with this device. We did this in almost 25 years ago in PSI for Shell, where we use this liquid xenon for radiation decay of vacuum. Later on, we moved to quantum vacuum because quantum vacuum is still something that, to my mind, we still have problem to understand. We have a big problem connecting quantum vacuum, cosmological constant problem, dark energy. So it's still there. I think for sure, we will have some surprise. So I moved to the quantum vacuum and later on back to the dark matter because is somehow related to the CPT conservation problem. You know that this CPT that was for quite a long time. This was made by Pauli and Wigner. Was a dogma that nobody cannot touch the CPT conservation, but you know that later on there was weak interaction, and so probably there is this type of violation, CP violation coming from strong interaction, and so there are problems there. So this is why I'm much more attacking on this type of approach more than your WIMPs type that most of you are making WIMPs. And so I will just, I'm experimental, so I will just introduce these axioms, from more from an experimental point of view, and later on I move most of my time in the experiment because this is what I like to do, and I did at least 3 experiment on this axiom stuff, and this is what I'm going to present. Just also give just an overview.
So Gianni, before you go on, so just to add, because he's a bit shy, as you can see, but he studied with Professor Conversi and then later with Professor Rubia. So I guess that this experimental feeling.
It was an important time. Later on, also Richard Parker, but it's okay. So I think we don't care about this. Means what is important. You see, this is also for you. It's most important. Just to try to have an overview. So instead of doing just for sure that each of us have to solve problems, but at the same time, just to try to have an open approach to a complete overview of what is going on in physics, or at least in what you're doing. So this is what you have to try to do in your entry career, but later on, hopefully, in your future career. So can I move on now? Okay. So I'm just to introduce back again a little more in detail from what Girelli was telling you about this axiom stuff. And later on, we will move to the experiment, how we can probe this axiom stuff is there or not. Okay. So we know that we have open question. Okay. First of all, this is also, you see, my point of view. We have on one side where this quantum field theory, that if you go back to the historical point of view, you see this theory was a pain for most of these brilliant people we have. You see, we move on from the beginning of quantum mechanics, and later on Dirac, you see relativistic quantum mechanics, and later on second quantization, you see Lambshift, Feynman's Winger, and Tomonaga. So it's really, it's hard to move on. It's really, it takes a long time, you see, respect to the general relativity that just grow up in a shot and was just there, and we use was very successful and so on. So I think this standard model of particle physics is mainly built up on this quantum field theory. It's very successful. You see, we start to move on with quantum electrodynamics. Later on, we make this a heteroweak connection, and with QCD, and we are still moving on. You see, the big success was this X, but the story is not yet ended. Okay, it's not yet ended because you see, we want to have this unified theory, trying to connect what we know from the microscopic world, what we see in the cosmology, you see, and this means that we have another approach, this standard cosmological model, that we enter into this business with cosmological microwave background, okay, and later on probably in the last century, we built up, we grow up our knowledge, and this our knowledge, you see, it's went looking into the detail of large-scale structure, gravitational lensing, supernova cluster, the light element abundance. So we have really a good panorama. Now the problem is start to match this overall knowledge and the experimental situation that we have in our hand, but still something is missing. Why?
Devi cliccare sul mouse.
Okay, so this is not the end of the story, because we know we have this portal coming from neutrino that is telling us that something else has to be there. Okay, this is something that at least we know is there, but the problem that how to move on and try to correlate all these problems. So these are the main. I'm going to just put all together there. So we have a problem, try to explain why in our universe we have matter, not antimatter. So this is one of the problems. At least that to solve this problem, we need evaluation of baryonic number, CP evaluation, and also some equilibrium condition from the beginning that just relax the universe in the matter situation, not in this normal, not in the half and half situation. So this is something that we still have to solve. And also we have an experimental approach how to solve it, which also I'm involved, but I'm not going to tell anything about. It's just making ADM, electron dipole moment measurement. Okay, so this is the way in which we can probe also new physics much beyond the energy of scale of large hadron collider. And the other problem is coming from, is somehow correlated to this matter antimatter problem, is related to this QCD Lagrangian, in which I don't see there is this CP rating term that is coming from what I measure for the ADM of hadron, means for neutron. Okay, this, I will be back to this, and this show up this variation in the strong interaction, and later on we have to correlate also the other stuff we at least that we know that has to be there something. Okay, means dark matter, dark energy, and inflation, and so this is we have to somehow try to merge this something that we don't know with this, let's say, standard model of quantum field theory. Okay, so this is and making this I think we will take us for much longer time, I think, and for sure there is this the system that we have to take care at the same time, gravitational supersymmetry, grand scale unification, and then try to think how to probe the scale of this equation. Okay, and this is now we are going to just to focus on this a QCD problem that will help us to solve at least few of these problems that I just showed you before. Okay, naively, you see why people tell us we have quark, the protein is all protein neutral around GB, well, C squared, the mass equal to mass, we know that quark, many type of deep inelastic scattering, where in our quark in the proton and neutron of NeV scale energy, most of the rest are on the gluon type of energy. And so if you naively imagine that you have this neutron stuff, and you think that you have this quark content, and this you say that this you have the different charge structure inside the nucleon itself. So if you just take a distribution of this charge that is just different of 1/10 of the radius of the nucleon itself, you expect that the whole moment should be on the order of 10 to the minus 14 electron per centimeter. Okay, this is the scale that one should expect to see something there. Okay, and we know that at least we know means we measure that this dipole moment of Newton is of the order of 10 to the minus 26. Okay, and this is funny because who started to move on this problem was to these two Nobel Prize physicists in the United States, more or less in the time where there is this dogma, means that you cannot touch CPT theorem, and they measure this on neutron, okay, with much more poor experimental resolution, but at the time also was the time when the around 50s that weak interaction with TV and Madame make the experiment just short that there is you have parity non-conserving interaction in the weak sector. Okay, so this is from that time on, you see, to build up, we are speaking around 60, to move on into the strong interaction was quite a mess. I think it's something that is still now, it's a mess to handle all this means a strong interaction. Means when I say handle, means from theoretical point of view, okay, because you have gluon, you have chloro, you have quark, and put it all together and try to make it's not QED quantum electrodynamic, so it's much more difficult. But you see, there was a problem of confinement, but we succeeded at the end also to build up means to unify with the electron weak also the strong interaction. So we are just in a good situation. We have this overall field, okay, this boson field that we know that photon, okay, Z and W, and this gluon stuff, and we are in the situation that you can arrange computation and just check. You see, a lattice QCD was very successful to give the mass of the atom. Okay, this was a big success for the QCD. And what happened there? Okay. You see, che faccio? Vado a mano? Ma non lo so perché si stoppa ogni tanto. Okay, so okay, I was telling that there is this problem. Okay, this problem is because this problem was this ADM problem is related to the Lagrange piece of this of the QCD that take care of this gluon stuff, and you have a parameter theta, an angle, okay, in which you have to handle in such a way to bring this in a very low value. Okay, so when you have an angle, how you probably have seen how you handle if you want to make from angle to a particle. You use a complex number. The complex number you have amplitude and phase. Okay, you can manage. So this was the idea from Peche Queen, try to translate this problem of this theta term that has to be very small because we don't observe in the neutron, the dipole moment is far away on the order of 10 order of magnitude also more from what we expect, we naively expect. Okay, and so there was a problem how to explain this experimental situation, this measurement. Okay, so this is you see, you can rephrase this dipole moment of the neutron as something at the scale. Okay, this in 10 per centimeter, somehow let's say the naive scale dot this angle that have to come out from the prescription of QCD, and this the actual limit is on the order of 10 to the minus 26. So this theta term has to be less than 10 to the minus 10. So this is a funny situation that within quantum field theory you have to explain. So this is something really we are in this quantum field theory. There is a problem. How to solve this problem? Okay, and so this is a more. I'm not going to. You can move up, try to weigh at the same time this theta value also with interaction, but this is something I think is not very important for us. So, allora, the problem is this: why this angle is so small? Okay, so there are at least 3 solutions to this situation. Okay, and the first one, let's say, anthropic principle. That this is my feeling. I don't like it very much this anthropic situation because we are too much in the center of the universe, and this is something that is disturbing my mind. So, but in any case, anthropic feeling of that we are here. So there is a fine tuning that give you this theta so small. Okay. The other approach that there is a CP that is broken spontaneously, this induce this theta at very small value. But this approach give problem with cosmology. So this is also we're not very happy about because there is a bad interaction, bad negative interaction from cosmology in this way. And the other way that is much more, as I say, this approach was coming from Peche-Queen, in which I connect this angle with a global symmetry, means to a field, means to a particle. Okay, and this is a way to try to solve this problem. The problem now, how to connect this to a new field. Okay, so this is a way in which there is an angle. You see on the left side, you have the static CP relation angle that is almost close to 0. And I was telling you that how an angle can become a field. You use a complex number in which you introduce the phase, and the phase is somehow related to a field, and so you can rephrase this theta angle as an axion. You see the axion field over a coupling constant. Means this FR tell us at which energy scale this phenomena is coming in. Try to solve your problem. Okay, and this is this means that I can write this theta term in the standard QCD Lagrangian in this approach in which you see it appears this axion field over a coupling constant, and this is somehow related to this Gauss-Gaussian axion field. And this was just because the Peche-Queen they introduced this approach, okay, to solve the problem. But was Weinberg and Wilczek that showed that this has to be connected with a real field, means particle. Okay, so this is was the step, and Wilczek just gave the name of Axion because there is just a solvent that you can find this in the US supermarket that was called Axion. Okay, this means they clean up the problem. Means this is the idea. So you have a soap that clean up the problem. This was the where the meaning of this axiom term. And this axiom just particle. These are just an excitation of this field, and this is also we have on QCD that the mass of the axion and the coupling constant has to be equal to the mass of the pion per coupling constant of the pion field within the nuclear, within your hadronic sector. And now we have also the QCD relate the mass with axion field. You see, the axion, we can write down that the axion mass is the order of few microelectron volt dot the scale of 10 to the 12 GeV over this coupling constant. So if I want to look for an axion mass of a few microelectron volts, means that I'm looking to the energy scale process of the order of 10 to the 12 GeV. Okay, so this means that you go very close to the good, means nearby to the Planck's energy scale. So this is why also at least it's attracting to me to go in this direction. You say so. There is many situations that is pointing out trying to solve this problem. That this problem just within within this our way to the quantum field theory. Okay, so this is why I think at least to me it's appealing. Okay, so this is just to say that the axion can be used to solve this strong CP problem in QCD, just explaining why this the ADM electron dipole moment of the particle that could be hadron or lepton is so small. This axion could be also means a possible source of quantum matter in cosmology, because a light axion cannot decay. Let's say so. It's a really stable one, and has to be there for the universe time. And also could be a source of this source of matter antimatter asymmetry, and also they are dreaming to use also this axion field driving the inflation. Okay, because also there it's the inflation everybody seems that digest, but it's something that is at least to me as experimentalist, it's very hard to digest this inflation field. Okay.
You said the axion should be light, so it's stable and doesn't decay. If it's heavier, what would the decay do?
Yes, we will. I will show it now.
Sorry.
Yeah, no, don't worry. It's correct. Okay, so this is, I think, it's a good opportunity. You see, we won't start solving many situations. Okay, so what is happening? This, you see, this Pacheco and Balmer, which paper came out in around 77, 78. At that time, you see, there was not the idea about this Woodruff zeta. The idea that this particle was living at the electron scale around 200 GeV. Okay, so it was the experiment that sent in the Slack trying to see this particle at this electron scale, and this means the axion mass of the order of 100 keV. They don't mean this particle didn't show up in this type of experiment. So the people start to be a bit anxious about this fact that was not seen over there, but just after, you see, after a couple of years, almost immediately after this experiment at CERN, there was a plethora of theorists in which show that you can make actions that are very light. Means very light means that this coupling constant is very large. So you boost this FR coupling to this 10 to the 12, 10 to the 15 GeV stuff. So this means that it became very light, became non-decaying, okay, and it could be also usable for this dark matter solution. And this is we call appunto, most of these people call invisible axion, just because it's very hard to try to detect, try to make this type of physics, just because the coupling to the standard matter is quite hard, or field is quite hard. We will see this later on. So this is, I told that this was pushed, this invisible axion model was put to the very grand unification scale. And this was okay. It was called invisible just because most of the experiment that was done at that time was not checking this axiom. And later on also this axiom also was used still used a lot in the string theory, in Gutenberg and many other stuff. And what the people realized that this could help or could be connected to the cosmology, stellar evolution, to new long-range forces, could be made could be produced in a laboratory, and also could be also a main component of dark matter. Okay, so this is, you see, with one guy we can solve many problems. Okay, and this is the type of interaction that we have to deal with. It means if you want to produce or you want to probe this axion particle, you see this is the standard interaction, the axion in which you have the axion and the coupling constant. This is the coupling constant, and you can couple to the quark, to the gluon, to the photon, and to the lepton. Means this side means, let's say, hadron, this side lepton, this side boson means photon stuff. Okay, and when you probably, I don't know if you mean, when you see a gamma phi means the spin around. Okay, and this is the people start to look a bit more in detail how to connect this interaction to a possible experimental situation to produce, to detect, and so on. So, okay. So this is the let's say the standard, the more standard way to look at the axion. One is through the photon axion to photon coupling, and this is, you see, the Lagrange, there is the axion field, okay, with the coupling constant to the photon, and this is the scalar product A dot B, okay. I don't know if now you are a bit handling a bit of theory. If you have a term of CP violating term, and you have to build up an Hamiltonian that at the end of the CP dot, this Hamiltonian have to restore the overall situation, means that the only way in which you can build up this Lagrangian coupling with the photon is the electric dot magnetic field, okay, scalar field. This is the way in which you restore the overall situation, okay? This is if you go to a photon approach. If you go to the electron, you see this is, you have the axion to the electron, but this coupling is going to the gamma phi, means you are going to the spin. It means that the axion, in this case, probably we will see, is going to interact with the gradient of axion field, okay? And to get a response of the electron, the standard way means you are going to have a spin field. And this is a way which also will work on this axion detection. But the problem that with this axion electron coupling, in terms of detectability, is much harder than the axion photon coupling, because also these two models that we have, you see, they are just not too far away each other. So this is the standard way to try to detect this through this axion to photon coupling. And this is okay. This is the question. This is you see here. If the axion mass is latent than to axion to electron mass, means you can just compute the lifetime of the axion going to photon. Okay, and so this is tell you that this tau is much larger than 10 to the 17 seconds, so it's much larger than the universe time. So this is for the interaction, and then if we just move on in cosmology, you have to just to realize how this axion can be produced in the at the beginning. When I'm saying the beginning, there is a story pre-inflation or after inflation. This is not yet clear. I will tell something more. I will tell you where I'm more attracted on. And because you see, you have this a production that because this is easily connectable because in Axion it's built up in the strong interaction. Means this action came up from global fork interaction. Okay, but if you go this way, these are too hot, and we don't like. And also with the evolution, it's too hot. So this is a bad way to produce and give a dry concentration in the aqueous situation. We need something in to be usable in the colder matter in such a way to build up this halo, the structure, and so on, so on. And so this is going. You go to the. I take the name and I will try to explain the physics underlying this idea. What is called the vacuum realignment mechanism. So the name is a funny one, but I will tell you in another way. You know, this is we say that is a field. Okay, we can plug this field with an equation, and usually with the wave equation. Okay, which you have the derivative of the field line, a bit like Maxwell type. Maxwell type, you know, that is linear in time. Here you build up an equation also in the second derivative in time, in which you have the field, space, in derivative, second order, and you have a damping term. Okay, you see, like oscillator, you have a damping term. So now, in this process of universe expansion, okay, you have this wave equation with the damping term related to this to the axion mass and with this coupling, and there is a damping term that give you the evolution from a theta term that is different from 0 to something that is going to become theta equal 0, and this is related to the damping term that is related to the expansion of the universe, Friedman equation of the movement of the universe, and this tell you how this theta term is going to relax to theta almost to 0. Okay, so this is what is called in the intern vacuum realignment. Okay, that is related, you see, to the false vacuum. Usually, you need in our Hamiltonian, we just make we have a picture of a simple vacuum. Okay, if you want to break, you see, like probably you have seen many of these cartoons with this hot, that means with a Higgs vacuum potential. Okay, so you break and you can have a vacuum term somehow like the Higgs at top potential. Okay, so this is something similar that is happening to this. This is somehow related to the broken symmetry. It means number goes on boson, how you break the symmetry. Okay, you come up with the with particle. And okay, so apart from this situation that is very tricky, okay, that you have to go at the beginning of the universe, this is later on you have to make something more, means that you have to try to understand, if possible, if this axion field is went to 0 just before the end of the inflection, means in the pre-inflectional era or after inflation. And this we don't know. Also because, as I told you, inflation is still, at least to me, it's something. It's not for easily to digest for this fast expansion. It's really a delicate subject there. But in any case, we have to. We would like to know where it came out. Okay,
So this means this theta term was going to zero just before or after the inflation. Because this, you see, just answering to this question, we know where to go and have a look for the mass of this particle. Okay, and this is the problem. And here, because if we are thinking that this particle came up just for this vacuum line and went to zero before this in the pre-inflation time, this is I have three parameters. This theta angle and the mass, and this means that I cannot say anything about where the approximate mass is. I have to look into this building. Okay, this is really a hard situation. Okay, it means for theorists and also for experimentalists. It means because you don't have any indication from theory. I belong to the widget approach, saying that this guy appears after inflation. If they appear after inflation, you can deal with lattice QCD. Lattice QCD is very powerful situation we have, and this lattice QCD in this post-inflation scenario with just one free parameter, and so just it's a question to work on this huge computer. Fantastic to make a lattice mesh as fine as possible, and the last output from this lattice QCD calculation to last the mass of the actions to be between 40. Now this is went down between 40 and 120 microelectron volts. Okay, in terms of frequency, okay, I replace in terms of frequency, 40 microelectron volts means 10 gigahertz. Okay, later on we will move from energy to frequency. Okay, 40 microelectron volts is 10 gigahertz. Okay, so this is and this is also which is pushing means saying to the experimentalist it's better you go in this direction. So I appreciate him a lot. He knows a lot of physics. Now I think it's one of the pope of physics after Weinberg. And so I say, I follow what which, because I'm not so powerful in my mind, I follow what which is just suggesting us. Okay. And so this is this means that this is a region in which also with time probably the people are going to reduce this region, because we will see that this is it's quite hard to go and move through all this region. Okay. So now we move to experiment. So now I try to just to shine your mind with what I have in my mind. Okay. Now the problem how we can detect. Okay. So I told you that this coupling constant, this is the real problem, is so weak. Okay, we're speaking this coupling constant 10 to the 12, 10 to the 14 GeV means microelectron volts scale.
You're about
half a year also.
Would you like to ask for some question on the first part?
I don't know. Okay, so why not?
So if the axiom can decay photons, I would expect it to decay no matter how light it is, right?
Yes, the problem that is the lifetime of this
Okay, so
it's not a good channel to see.
Okay. But as soon as electron hooks would be open or quarks, then it would be, you could not push the coupling so small that it's
No, it's hard to go into the decay. Okay, just if you think to make an experiment of decay, also if you have a decay of this other stuff, the decay probability is so small that it's quite unimportant.
Any other question? I'm sure that you have question on Axion phenomenology.
No, I think I think it's I'm here for just for you, just trying to tell how I see this world, because I think this is also you have to make this effort to try to have
try to have a larger vision of where you're looking, what you're looking, what you're hopefully I'm going to see.
Okay, so everything was pretty clear. We'll collect other questions.
Yeah, allora, this is I was saying that we're going to use mostly for this search, this Axion photon coupling, and
Gianni,
this is
please don't forget the-
yes, this is the case as a Primakov effect, because Primakov effect, we know that we have an energy gamma going nearby Z, mostly Z nuclei, so it's coupling with the virtual photon of the Coulomb field of the nuclei. You're going to produce a pi zero, and later on this pi zero is going to photon. And so you can make the reverse, okay? If it is axion, because the axion is a cousin of the pi zero, you can make the reverse using this instead of you can also a Coulomb field. The problem with the Coulomb field, the de Broglie wavelength of this cosmological axion, they are not fitting together. So you need to have a larger electromagnetic field with which this axion is going to travel through. Okay, so in presence of the external field, that will be magnetic electron, the axion and the photon mix, and this means give rise to oscillation, means convection. So you can convert an axion to the photon. This, as we have seen before, this is axion field A dot B. It's the source of the electromagnetic energy, because you have to remember Maxwell that tell us that between B and A, with the magnetic field and electric field, there is a C factor. So usually having a magnetic field, you have much more energy density with respect to the electric field. This is why most of the experiments they look for high magnetic field. Okay, my magnetic field means 10 Tesla. Okay, 10, 14 Tesla is something that is affordable. Higher than this, I will tell you later on that it's problem to get higher field. It's possible, but the problem that the cost is very huge. Then I will just go through when you will see in paper, there are many papers speaking about axion-like particle or WISP, but this means that you do not have as axion QCD the correlation between mass and coupling constant. So these are three parameters. So you can look whatever you like, okay? So this is something that most of the people are looking to this, because axion is very hard to go to the QCD line, and so you see this axion-like particle, okay, in which you have no connection between this. And the same, you probably there are paper about this WISPs that weakly interact with spinning particle that again in this family you have the photon, middle charge part, the chameleon, and stuff like that. So also there are effort, experimental effort, but this is usually you have some experimental device that can say something that people use to try to connect and try to publish something, but it's really hard that these are really not directly connected with QCD. So moving to the detection strategy, okay, there are at least the laboratory experiment means that you can make a polarization experiment, light shining through the wall experiment, a fifth force experiment to try to say something on the axion. Later on, there are solar helioscope, the dark matter helioscope, and also you can infer something from astrophysics, cosmology, stellar evolution, gamma ray transparency. So this is you can plug in from the signal that are coming from the units. Okay, so we can just these are the three main directions. You see, production and detection actually in the terrestrial laboratory, and you can go through polarization experiment, and light shining through the wall experiment, from this axion detection in which you use sun as an axion production, okay, or you can just go to try to detect this axion taking part in this dark matter situation. Okay, this is our current situation on the current constraint axion photon coupling. You see, this is axion mass versus axion photon coupling. This is the axion line, okay, QCD axion line that connect mass and the coupling constant. And you see that many of this, the knowledge we have, you see, is far away from aligned to this QCD axion line. The only approach that you have chance to go there is through this haloscope, okay? But also there are problem, okay?
Can you go back to the last slide?
This one.
I know you never detected these particles, but so can you estimate a flux we are going to receive?
I guess later on we keep some number.
Okay.
Okay, for sure, we keep number. Then the problem is to go to the lab and try to make this experiment and look where you are. Okay, this is where we're going to see. Okay, this is just to say that you see the light shining through the wall experiment, you see, are really here. So loss of polarization experiment, they're really far away. Many of them are far away. The helioscope means using solar as axion production situation also here. And these are the hope, but to use haloscope, but it's also there. We will see that it's a bit hard to go there. So just if you want to make comparison between laboratory experiment, helioscope, and haloscope, you see, this is mostly they just check axion line particle. These are white band experiment, and they use optical photon. These are model independent, okay? The helioscope, they could cover also some QCD axion line. This is white band experiment, they use X-ray photon, and this is model dependent. And instead the haloscope that you hopefully you could succeed to say something about the QCD axion are resonance experiment. They use microwave photon, they are strongly model dependent, and they use means the axion flux is very high. So you see, if one rephrase, this is a low sensitivity to axion like particle coupling. This is a good sensitivity to ALP and to high mass axion. And these are really if the dark matter is constituent, is 100% axion, this is the good chance to go there to the QCD axion line. Okay. So this is
Gianni, just a question on this.
Yeah.
Basically, what you mean on the right side is that this haloscope has a very narrow wavelength to explore each of them.
Yeah,
So
because when I'm saying a resonance experiment, means that you have to pick up a signal from a microwave cavity or from a resonator that have a very high Q, and this jump in such a way to enhance the signal, and this means usually take time, and this is a problem to have a good scanning.
My question was more, why the next experiments have such a low sensitivity? Because you showed the
Because it's going to the G to the fourth power.
Yeah.
The probability to produce and to detect is going to the fourth power of this coupling constant. And you know that this is already terrible. Going to the fourth power, it's really reduce the signal a lot. But I will tell you in a while. Okay. Okay. So this is we go first to the laboratory experiment. Laboratory experiment means the polarization shining through the wall and the fifth force measurement. Okay. The polarization experiment, there was a paper made by Gianni and Martini trying to measure, you know, that we are in the quantum field theory. QED, we have this fluctuation. If you have, this is a 4 photon scattering vertices that you can compute and can you try to measure. Okay, so this is the people are doing this type of experiment is more than 30, 40 years, because you would like to see this and use of Fabry-Perot in such a way to increase the number of photons you have in the magnetic field, present in the magnetic field, and try to detect if this vacuum, the interstellar attraction, if you of the vacuum have some extra term. These extra term are induced by absorption, you see, through this phenomena, photon, okay, real photon, that is a laser photon. This is photon, a virtual photon coming from the magnetic field, going to axion. This is absorption, and this is related to the decreasing of the measuring the decreasing of the beam, or you can just have a dispatchon type of measurement in which you have this this type of phenomena in which you plug in the axion, and this you measure ellipticity of the beam that is transmitted through the magnetic field. So this is you have to measure this delta n for the ellipticity and from the delta kappa for the decreasing, and the QED tell you that this phenomena just for the a photon passing moving into the magnetic field is at the level of 10 to the minus 24 Tesla to the minus 2. Okay, so this tell you that also this effect is very hard to measure, and this is you can relate the previous you see this vortices, this vertex into a measurable effect in terms of ellipticity and decreasing, and just measuring connected to the axion and just measuring the both of them, you can just say something on coupling constant and on the mass. And so this means that you need a high magnetic dipolar field, because these two observable are going to do the square. You need an optical cavity just to amplify the signal, means that you use a Fabry-Perot in such a way you have you pass you increase the number of photons staying into the magnetic field, and you need to have ultra high sensitivity polarimetry to make this measurement. And for sure, you are going to modulate because you want to be out of DC phenomena. These are the experiments that has been made in the United States. There is in Tolosa, at CERN, and also in Italy, here nearby in Ferrara. And the idea is to have a laser, okay, going through polarizer, going into mirror, then this is a Fabry-Perot mirror, and this is magnetic field. The magnetic field is going to turn around in such a way to go into this AC measurement, and later on you have at the end a beam in which you detect with photodiode, and this is the transmitted beam, and you try to modulate this input beam with some other, with just turning around the magnetic field and just sort of modulating the elasticity of the beam. And this Gianni tell you that you need to have a large number of photons within the cavity, the length of the magnet as large as possible, the B square also, this B has to be, and this is inverse to the photon wavelength, and this is going to be modulated at twice the magnetic field is turning around the polarization axis of the field itself of your laser photon. So where we are now, you see, we are very close. Means these are the people of Pimulas. They are very close to this QCD prediction, but you see this line is just has been obtained after 5 to 10 to the 6 second integration time. So the integration time is huge. So 1 day 10 to the 5. So around this, it's almost 2 month integration time to get there, and they are not yet within this. They're not yet seeing this value. But this you can rephrase this in terms of coupling constant versus mass, and that you just give this limit to the axion-like particle situation. This is the setup that is sitting in Ferrara, and these are, you see, this is the magnet that are just turning around, and these are all the optical table laser in which you make this type of experiment. And the next approach is the one that was proposed by Carugno, Sikili, and Van Bieber, in which you use a laser, you go into a magnetic field, and here you produce axion, you have a wall, and later on this axion enter into a regeneration line in which again you have the B field, and here hopefully you have a photon coming out, and then the end you have a photodetector. So it's important to have a large magnetic field, the length of the magnet as long as possible, a good photodetector, a lot of laser power coming into the system, okay? And now this is, you see, going to meet your answer. You see, this is the probability that the photon, this is gamma, is moving to axion. And later on, the axion is passing the wall and is going again to photon that I can detect. This probability is going to this G to the fourth power. And this means that Bruno, you go down very fast with the sensitivity, okay? Because this G factor is 1 over this coupling constant that it's very small, okay? So this is the conventional probability in the magnet is 1, okay? It's related to this coupling constant with 0 to the square, the length of the magnet, this ratio that is related to the axion mass, photon mass, and this tell you that you would like to have very magnetic field, long magnet, high power laser, and ultra low noise receiver. This is also the most different experiment done on this approach, and still let's say the more the one that the people are promoting, that is really a huge effort, is the one that it's sitting in DAISY, in which they have, you see, something, I will put the number, okay, this is the sensitivity, okay, again for this coupling, and so you need a large field, long field, the probability is it's again related to this 4 power, the finesse of the cavity means has to be as large as possible, this is integration time, and this is the number of photon and the photon energy of the photon. So this is, they use, you see, the hair magnet is about 100 meters. They make a cavity, a fabric cavity almost 100 meters, a bit larger, in which they introduce the laser, they increase the number of photons there, so they increase the production probability of axion, and here again you have another 100-meter magnet, and later on at the end you have a detector. Okay, and so this is there are something that I'm not going to detail, but in any case, this can be done also in microwave regime. But at the end, here there are the situation, this coupling versus mass. You see, this helps. It's more or less here. Okay, if they're going to make this run with all this very complex setup, they will succeed to arrive here. So still far away from the QCD axion, but this is means a really strong effort that they're doing there in DAISY. And then there is another approach that again was suggested by Wilczek, because if the axion have this mass of the order of micro electron volt, big electron volt, you know that I can connect a mass with a compact wavelength. Okay, so means mass of the order of micro, let's say 10 micro milli-electron volt means a Compton wavelength of the order of centimeter. Okay, so this means that you can try to see this kind of field accepting some type of forces on some device. Okay, and this you can make this coupling to the spin, hadronic spin means proton nuclear, or to the electron spin. And this is what we did, and this is the idea. The idea was suggested again by Wilczek, and so you can be really a tabletop experiment. And the idea is the following. This is the coupling we use. Okay, so you have a source that we use lead, let's suppose lead cylinder, and this lead cylinder is the source of axion. Okay, if the axion mass is of the order of milli-electron volt, means this field is going over. It's moving over centimeter distance, okay? So this is, you can couple this axion field with the electron, and here we use a paramagnetic crystal, okay, gadolinium silicon oxide. And this is the potential in which you write down this coupling between electron, the spin, and the source. And this term, you see, you have a spin and distance. And this you can rephrase this potential like a mu dot b with this sigma of the electron. So means that this type of experiment, they need to be sensitive to field. Means because I have spin, electron spin, or you bring you know the Bohr magneton. So if you have a free electron, so free electron means a piece of matter or paramagnetic matter, and you have this axion field, and this axion field try to push the spin of the electron of the nucleon, and this means that you build up a magnetization. Okay, so if you have a good detector for looking for magnetization, means you can say something about this field, okay, and this axion field, and this is what we did. We did in this way. You see that this is the cryostat. In this cryostat, there is this paramagnetic crystal with the pickup coil around in such a way to check if there is any magnetization produced by the source. You see, these are many LED cylinder just nearby, because it is the constant wavelength of the axion, nearby to the crystal, and you check via squid if this your crystal is going to with the frequency that we decide to build up a magnetization. Okay, this is what we did. Okay, you have to use a squid. The squid level we succeed to work with is on the order of 10 to the minus 16 Tesla square root of Hertz, so you can make integration. And at the end, we give a limit here. You see, we give, this is what we measure. This is in terms of distance, that is mass of the axion. So we went down to, this is on the order of meter, this is a centimeter. So we were at the level, covering this our experiment that we did, and just to show you that this is 10 to the minus 10, that is the famous 10 to the minus 10 term. So we are still far away. We know how to move here, but take time, and we have too many people, you see, whips, so we are not enough people in this time. So please, so we know how to try to move from here to here. Because here there is something very interesting. Means if the experiment will succeed to go at the value of 10 to the minus 14, means we approach the you know that the Kobayashi-Maskawa term, there is phase that introduced. We know that there is a source of vibration there, but it's very small. So if you succeed to make experiment going down to this level, you should be able to check this term coming from the Chi-M matrix, okay? But this is, really is quite hard, okay? This is what we do. We publish a free paper on this. These are the last results we publish, and this is here, the overall result, okay? So now we move on the helioscope, okay? Helioscope means that because the sun, you see in the core of the sun is a plasma in which with a plasma temperature of the order of 10 kV, okay? So this means that you have nuclei, okay? That all the electrons strip out, means with electron around. So this plenty of photon, black body photon, that also X-ray. This situation means that there are a lot of this photon going nearby the Coulomb field of the nuclei inside, and this is the way in which you use Primakov effect, in which you have gamma, Coulomb field, axion, okay, axion coming out, and this this is the source in which you produce axion in the sun, okay, and this you come on the detector, means that the dipolar magnet on the Earth, in which you try to convert the axion to X-ray photon. Because why X-ray? Because this is the energy that you have inside the sun. And so this is, you see, more or less the spectra, the axion flux that we expect versus energy. Okay, so the peak is on the order around 4 or 5 kV. So this is and this is the flux in terms of this coupling constant. And this experiment is again the conversion probability is going from this coupling constant BF square, and this is a form factor, and this form factor is somehow related to the energy of the photon, the mass of the axion, and also the figure of measure of this experiment means that you need high field, long magnet, large bore, ultra low background X-ray receiver, and you have to track sun, means you have to track the direction of the sun. This has been made in the CAST experiment, Solar Axion Telescope, in which they use a 10 meter 9 Tesla LHC prototype magnet that you can move and point to the sun. And this is with this they succeed to put this exclusion plot. You see here, they're just here again. They are still far away from this. From this at least from this QCD line, okay, and they hope to move on this IAXO experiment, but it's hard to make the experiment. It's hard to make the magnetic field. So they're still looking, hoping to get money, hoping somebody that is going to build up this magnet. So it's still there is an idea, but there is group people around there, but I think it will take quite a long time before they succeed to make this prototype. And now we move on to this haloscope, and there are the IDMEs that means the oldest experiment in Axion stuff. We have our experiment, the electric haloscope, but there is a lot of experiment there. So back to the Goldman-Darmatter axion. You know that through the dynamics of the nearby star, you can infer this famous
It's actually a technical question regarding some of the microwave cavity experiments like DMX. You mentioned that when it comes to the eigenfrequency or what energy we're trying to measure, you can change that, but it only happens slowly. Why does it happen slowly?
I will go there. I will succeed to go there. Yeah. Okay. So this means from the dynamic of the nearby star, you can say which is the local density. You have this famous 0.4, 0.45. This is something that, and later on also you can just say about the dispersion about this the situation, and this is quite the dispersion means the dispersion because you have to take care of the galaxy frame, the Earth frame, and this is famous 270 kilometers per second. That means that the dispersion, the beta, is of the order of 10 to the minus around 10 to the minus 6. Okay, and this also just have implication of the scanning rate. Okay, and so you keep in mind this number, and these are this is the situation that you have to plug in for making an experiment. So you have this number, okay, around this density. Okay, this means that if the axion is a dominant component of galactic dark matter, means the occupation number of this axion is huge, you see, because if you normalize to 10 to the minus 6 microelectron-volt axion mass, means that you have something like 10 to the 14 axion per cubic centimeter. This can be treated as a classical field, okay, with a frequency given by the axion mass, okay, because the occupation number is so huge that this you can consider just like a classical field, oscillating field, and you have to take Gianni with the frequency related to the mass, and later on you have to consider the coherent length and time. It means with the coherence length that on the other you see with a kilometer for the mass of 10 to the minus 6 electron volts, and with the time for the order of few milliseconds. It means that you can cover your experiment could be in time and in space of this dimension and time. So this is the idea that was cooked up by Sikivye, and the idea that you need a cavity, because what you have to search, you have to look for real photon coming out from this cavity with the energy that is the axion mass. This is the let's say the axion mass in thermal energy plus this term that is related to the axion velocity, but this term on the order of 10 to the minus 3. This is dispersion. This is later on imply what you can do with the cavity. Okay, so you need to use a microwave cavity to enhance the signal. Okay, a cavity must be tuned to the axion mass, and this because this is unknown, because we don't know the axion mass, the tuning is necessary. It means that this is very time consuming. Okay, and what else? What means the signal I expect that I have to see on top of my noise a peak. Okay, with the bandwidth of the order of sorry, 10 to the minus 6. So and this is the probability for this conversion process for axion to photon is going to the b squared to the field in which I have my microwave cavity, the volume of the cavity, the Q that the axion Q if it's possible, but this is quite hard. And this is somehow something that I cannot put my hand. It means my hand means as a laboratory guy, I can put my hand here and on noise detector. And usually, you see, this is the big problem. The problem that if you want to make this kind of physics, you need receiver on the 10 to the minus 23 watt. That for this photon energy means that you have also probably less than a photon per second in this regime. Okay, so how this is the general formula we use. You see, we say that this the power, the axion put in the photon is of the order of 10 to the minus 23 watt in terms of this coupling constant, of density of dark matter, frequency of the cavity, B in which you have the cavity, the volume of the cavity, the mode of the cavity in which you are going to make the conversion of axion to photon. This is the Q of the cavity, and this is coupling of your antenna to the cavity, the beta. So you need a pickup to bring the photon out and go into the amplifier, and so you have to somehow deal with this power axion conversion with the noise that you can have in your laboratory, and this noise using linear amplifier. I will show you that we have in our hand now photon multiplier. So you see, you are looking, you play with a few electron volts. We are playing 10 to the minus 4 electron volts. You see, so and I think this is related to all this world of quantum technology. It means really you have this in your hand, and this will be really useful. But in any case, the P noise is somehow related to the temperature of the cavity, because the cavity is a black body source, is an oscillator that sits in the thermodynamic buffer. So knowing the frequency, you know Bose-Einstein channel distribution, you have to go at the temperature in such a way that the black body temperature at the frequency of your cavity is almost negligible. So you have to remove this type of contribution, and later on there is a contribution coming from the amplifier noise, and this is the bandwidth. Okay, so this is usually we refer this as gain Boltzmann system, that it's the sum of a cavity amplifier over the bandwidth. Okay, and this is if you use a linear amplifier, you have to use the Dicke radiometric equation. Means Dicke tell you that how the signal to noise ratio that you can use is just related by the ratio of power axion or to P noise, that you can replace at the P axion over this system temperature that you have on your system plug the measurement time and the bandwidth of your system you are picking up the signal. And the problem is here that, okay, this is for just a single frequency, but later on you want to move the frequency in time, and you see moving the frequency in time, you see you go to this power of the Axion to the square, divided to the temperature system of the square, and divided by signal to noise ratio in the square. So it means that this is became harder to move faster to make this type of measurement. Okay, so this is okay. These are just the first structure. You see, this was 87. Was Medicinos in the United States starting to go into this business, and these are the main components for making such type of experiment. You need a dilution refrigerator with a base temperature in millikelvin just to remove the blade body photon within this oscillator that is electromagnetic cavity, and at the same time also because you want to operate means superconductive electronics, so this means that you need to be very cold. Then you need a cavity with a quality factor as close as possible to the Axion line, dispersion line with larger volume, and with the possibility to make a tuning, and to move around. This, you have to imagine that you have a radio, okay, like an old radio, you move, you see usually the capacitor and you scan, and you just look if there is something, excess noise coming out, okay? This is the idea. And then you need a larger magnet with active shielding, and here now we have 8 Tesla, we will have a 14 Tesla, and then you need a very low noise receiver. This is, I move on, this type of experiment has been done for photon detector using Rydberg atom, but this is it's quite hard, it's possible, but it's quite hard approach. And this is the current situation. There are the American, they are just in this type of the two leading, there are also some leading experiment, but the two leading experiments in the United States are the MX in Washington and High-Stack in Yale. We are in Legnaro, in Frascati. There are a large center in Korea, in Australia, and Germany. Means now almost everywhere there is Taiwan, China, everywhere there is a boost of this type of experiment. Okay, and here this is the situation for the experiment, and I'm quite optimistic because there is a large effort worldwide that in the next, probably it will take between 10 and 20 years. So I will be out, probably I will be already horizontal. But there is a good chance in this approach that took over this region, that I think is the most interesting region. Okay, and this is okay. This is the ADMX that means that they're starting scanning, and they succeed to cover mostly these two model, but in the frequency region at around a few hundred megahertz. And this is High-Stack, the other American, the Yale. They succeed to make a big step forward, because when I use a linear amplifier, you know, I have from the output two parameters, means amplitude and phase. Okay. And what they did, they make this squeezing, because you can, you see, you can just make a receiver in which you dump out one of these two parameters in such way to increase the other one. So they succeed to do this, and this is using this squeezing technique that it's not easy at all to handle. Okay, and so this is why we are not moving into this direction. And but also they are very good guy there, because there is also there's a large they have NIST, and there are many other people helping them. And this is the Korean Institute, in which they have something like 10 dilution units. Really, there is a big effort there. They are really, I think, for the time being, they are the best people in this game of holoscope, Axion holoscope nowadays. And because they cover, you see, from cryogenic, electronic, cavity, and the quantum amplifier, You see, these are all the experiments they are running in Korea. So it's really, it's very hard to be in competition with this guy. And this is our experiment that also we reach at 10 gigahertz this axion curiosity line for just few points. So means that we are able to go there with this, and we are starting. This is what we should say that is an interesting region. So this is what we are doing. This is Taiwan. This is another experiment, and I will just go through. Marco, how long have?
We have 20 minutes.
20 minutes,
Maybe we
okay,
can
so
take,
probably I was going to.
Including questions.
Okay, so just to show that there are many approaches, this is what is nice that you have quite the space for new ideas. It means because you are connected to the world of quantum technology, to the cavity, to the electronic, superconducting electronics. So there is really many groups that are trying to find out the idea how to put multi-cavity, read this multi-cavity at the same time. So there are many really people. This is a French group, going back to what I was saying, high field. You see, you can go really now doing field up to 40 Tesla, okay? Because if you use a standard superconductor, means niobio 13, you can go up to 14, 15 Tesla. These are magnets that you can close. You know that you probably you know a bit this superconducting magnet technology. So what is nice that you have a coil, okay? You have superconducting coil. You feel you have to charge up this coil. Means that you have two legs, okay, going down to the liquid helium. You have to be careful that don't bring too much power, heat power inside. How you charge if you have a superconducting coil means short circuit. You have a piece of these two legs that are going into the superconducting magnet that are embedded into a resistor. So if you want to charge up a superconducting magnet, you heat up this resistor. So you just in a short region you have you go from superconducting to normal state. Means a resistive state. Means at this time you can charge the superconducting magnet. Once you charge up the superconducting magnet, you remove the power that you apply to get a small portion of this superconducting magnet in normal state. In such a way, the current is flowing, okay, for really means can stay there month, a year, okay, with very small loss. And so you can play with this magnet up to 14 Tesla, okay? Because the problem that you can go higher in magnet using this new Repco tape. Repco tape means rare earth IPCO, you know probably the high superconducting temperature magnet, okay? These are Repco tape that are really incredible because they can sustain in a surface on the order of micron by 10, let's suppose that you have in 1 micron, 10 millimeter, okay, surface, you can fill up at liquid helium something like almost 700 or more ampere. Okay, so it's a huge, incredible amount of power that you can pack into this device. The problem is where? The problem that into the connection region. Means the connection region is dissipative situation. Means that I have a big loss in liquid helium. You know, the heat latent of the liquid helium is on the order of 20 joule per gram. Okay? And if you want to pump a lot of current there, you have also a small resistance. You have easily, you go, if you want to pump this magnet going to 40 Tesla, you have a dissipation that could be also 10, 100 and more, but means that you have an evaporation rate of liquid helium very high. And this means that you need electrical power to recondense this liquid helium. So just to give a number, somewhere I put a number, because the idea was to make with these people in Grenoble, which they have this huge field. This huge field means this 40 Tesla, and for making the experiment, you need to pay, means the experiment was the cost of electricity, because you need something like more than a few megawatt of power, electrical power, to keep going on this experiment. So it's, this is the problem for this large power magnet. Okay. This is Australia, with which they want to go to high frequency. The problem with high frequency that is related to wavelength. Okay, means 1 giga is 30 centimeter, 10 giga is 3 centimeter. If you move up in this, for me at least interesting region, you go into the millimeter centimeter. Means that the cavity became very small. Means the convection volume decreases a lot. And this is a problem for the power convection, okay, the Axion. So that you have to come out with some idea that there are around that just under development. And this is, okay, this is, if you want to make the experiment, you have to take care about this scanning rate, okay, that is related to this parameter that we described before. And this is related to the electronic. You see the noise I told you that is related to the cavity and the amplifier. So you want to go to the quantum limit. So you want to remove this, okay? This term that is Bose-Einstein term for the oscillator, just keeping this quantum noise level. It is possible, yes, it is possible. Up to which frequency it is possible? Up to 10 gigas. We succeed to operate electronic, means linear amplifier, up to 10 gigahertz at the quantum limit, in which you see this, the detector noise temperature was just the quantum limit, okay? So this is at the best you can have for making this type of experiment with this electronic. And so this most of the people move from this high electromobility that are just with the noise temperature, you see, on the order of 5, in between 5, depending on frequency, let's say on the order of 5 Kelvin. Okay, for 10 gigahertz, the temperature, equivalent temperature is on the order of 0.5 Kelvin. So if you want to remove from this oscillator, means cavity, the black body photon, means that you have much, at least 10 times lower in temperature, in such a way that the Bose-Einstein term that are in the denominator Canis kappa T is almost disappear. Okay, and so the people move, starting with this mobility effect, they move to Josephson parametric amplifier. The problem with Josephson parametric amplifier, they are just the bandwidth is quite limited bandwidth, and now they move to what they call Josephson parametric wave parametric amplifier. Means that they have many of these Josephson parametric amplifier in series in such a way to have a large bandwidth, and this is what we have. Then the other option is the squeezing, but to me is quite a mess. And I think what is a real future is this single photon count that we have. We are using. We did the experiment. I will try to show. Okay, this is the problem you see with this type of measurement. That you refer to noise in terms of z of r square root of hertz. Okay, and this is, you see, we work at 10 gig, around 10 gigas with this Q, with this magnetic field, with this volume. This means the power in terms of rate for the two different models, you have something like 60 hertz or 8 hertz of photon produced by the Axion, or the Axion there in the cavity that you pick up with it, and if you have your photon detector. We did a pilot experiment, I will show you with much in which this number was much lower. But in any case, you see these are, you see the different source of of noise. So this is thermal noise. If you have a cavity that works at around 50 millikelvin, this noise you see around 10 gigahertz is almost you have not to take care of this. Okay. The problem you see that is the quantum limit. It means the standard quantum limit is going up. This is the problem. So this is if you want to go up in frequency, you have to take care of this also. If you have very good electronics, so this means that it would be nice to have a counter, because with the counter means a photo multiplier in the microwave. That if you have already a photo multiplier with that rate on the order of 10 Hz with a quantum efficiency of 0.3%, you see you're already much below the standard quantum limit and thermal noise. And so this is why we need to go to in this business. That and this is what we did. And so the requirement for the single photon counting, that you need to pick up the photon and bring it away, because this is a superconducting device, and so they cannot stay nearby this huge field. So this has to be far away, and so you need to have a very low count, the quantum efficiency, the equivalent quantum efficiency of your photomultipliers to be quite high, and also large dynamic bandwidth, because you want to move through versus frequency. And this is the device that we are using. This is a device that has been made by the, let's say, you know that Haroche, this Nobel Prize, French Nobel Prize, he did this game where he developed in cavity. Later on, he was in École Normale. Later on, he pushed these people, these people in École Normale, to move to the quantum circuitry. Okay, so instead of using atom, that usually is quite messy to play with, to go and making circuitry, because in microwave you can make let's say artificial atom, okay, and you can play with the artificial atom on a backplane, on a circuit, and this is what they did, and they developed this device. Again, it's based on Josephson junction device. They made what is called a Tasman qubit. So this is you have a system that you prepare in a certain state, and later on you're going to interrogate through time to check if somebody is going to improve, change the ground state in the first excited states. This is the game through all this electronic measurements. But what it's I think to me very appealing that this group, you can just look to this paper, they succeed to measure through this technique single spin flip of the electron. So now we are able to hear electron spin flip of matter, single electron spin flip. So means that we are speaking about 10 to the minus 4, 10 to the minus 5 electron volts, okay? So 5, 6 order of magnitude what you're doing with your WIMPs, xenon, and whatever it is. So this just to say that I think that if we want to move on also to, let's say, like the matter, we have to move this way. Okay, so there are also other ideas, but I'm not going through. And this is what we did in Paris. You see, in Paris, we use this device. And so we connect this single photon detector, single microwave photon detector with a cavity at 7 gigahertz in a 2 Tesla magnetic field. And also we succeed to make a tuning. The paper is on the way. And we did this. Now we move with device to Padova, and we are going to build to bring this device in our illusion dry system in Padova. And these also the people. There was people in Chicago, in Fermilab, in which they use this qubit stuff for looking for dark photon. This device cannot be used as a photon detector far away from the cavity. This is just nearby the cavity, so this cannot be used really for Axion, for alloscope detector. And this is the people are moving, you see, to develop new microwave cavity. This is what we did. Our idea to use the electric cavity, because sapphire, the tangent loss of sapphire is at low temperatures of the order 10 to the minus 9. The idea with the electric cavity, because most of the loss, if you use a copper cavity, also if you use very good copper, whatever, clean copper, whatever it is, you have the skin depth that is usually limiting the Q value of your cavity. So the idea is to insert this sapphire cylinder in such a way that the electromagnetic field you push into the sapphire, and so you remove current from the copper surface. Okay, and this you boost the Q factor of the cavity. In this way, with this particular cavity, we succeed to go to 10 to the 7 Q factor. That is okay. If you are not into this domain with a copper cavity, usually you succeed in the microwave 10 to the 5. Okay, and also 10 to the 5 is not easy as a Q factor. So, but there is a lot of development in Korea, in United States, trying to develop beta cavity. And this is the Korean people using this Redco tape. They really succeed to do something incredible. They succeed to have 13 million of Q factor under strong field, because the problem that the standard superconductivity and magnetic field, you see, they don't love each other. Means usually under magnetic field, the standard superconducting material, they relax to the normal state, and so this is the main idea related to the cavity development, geometry, things like that. This is, I'm not going to say too much about this. And now this is the number, you see. Okay, if you want to see, you see, if you want to get this 43 Tesla in this very small board, you need something like 24 megawatt power. So this is so for the moment, I think it's something. I think it's something to make an experiment in Oregon or United States where there are. And also there is other approach that people are doing. Try to again, this is only a selection in which you can just look for the Axion, and this is just a few ideas, and I will go to some of these few ideas, but this is something related to what is called axion electrodynamic, because the axion, due to this coupling to the matter, you can put this term into the Maxwell equation. Okay, Maxwell equation, usually you have two sources, current and charge. Okay, in the Maxwell equation, and you can plug in this kind of axion as a let's say another source in the Maxwell equation, means source also that are going to discuss with the photon within the Maxwell equation. So many of these experiments are just using this axial electrodynamic approach that again was Wilczek, that was showing that this extra idea how to move on and for checking this axial stuff. And so this is many of these ideas use this axial electrodynamic approach that I know probably have no time, 1 minute, so I will just tell, okay, this is let's say the Wilczek group, how the idea to use a plasma alloscope to go into high frequency, and so you see there's plenty of guys around here, and trying to have idea to cover such a larger range of try to join this QCD line, I think. And this is, I think, it's quite nice because there are a lot of means instrument technology that you can push forward, you see? So this is, I think, is why I think this line, I think many of you can just to reconsider. And this is what we did with the Axion electron coupling. And probably I will stop here because again, you see the Axion coupling to the gradient, the electron coupling to the gradient of the Axion field, because you know that we are moving toward the Axion, okay? And so this means that I have a B field, a BRF field. So if I have a piece of polarized matter inside the cavity and have this Axion, and I have the Larmor frequency of the, let's suppose you have Zeeman, no? And the Larmor frequency equal to the microwave cavity, I can pick up a signal coming from the spin flip. Okay, this is the spin flip power induced by this Axion spin flip inside this electron polarized matter. And okay, these are the spin density, the minimum coherence time, the volume of the matter, the Axion. You see that we were speaking there around 10 to the minus 23, and now we're speaking minus 26. And so it's much harder to go this direction because there is alpha, an alpha factor. There is there is the connection, there is an alpha factor 1/137 that reduce this coupling. And so this is much harder, but we move on because I believe that this is not because I believe, because there are also many theoretical people that are just saying to use this collective excitation mode of the matter to make also some other stuff, okay? And so if you use this type of detector with a single counter, means that you can probably look really the small energy release within the matter, okay? And this is what we did, and we put inside the cavity, you see 10 of the sphere, of the sphere inside the cavity, and this was our PRL result, in which we succeed to measure, to went down to measure 10 to the minus 19 Tesla with this experiment. And these are again on the same line. Instead of going on the electron, you go on the hadron, means on the nuclei, and instead of using electron paramagnetic resonance, you're using nuclear magnetic resonance, means NMR type of experiment. This is the Casper experiment, and there are also some other experiment which you can pump with the Axion. You can pump excitation with your laser, and also there we did some trial and some experiment, and this is it's an interesting direction. And I'm just saying this, the last thing, I'm going to conclude just saying that we put our hand into in this time of quantum stuff. I think you have to try to handle also, means most of what you're doing means with detail liquid signal, liquid argon. Most of your atoms, you see, are means they're doing, they behave without not taking care of what's happening on the other one. Means you're scattering on your nuclei, scattering on your electron, whatever. So you see, they are not in phase each other. Means you see, when you make it, means in quantum field theory, no? When you want to measure cross section, okay, you have the dynamic part at phase space, okay. Now, when you go into the usually what you use in your experiment is you come out with rate equal cross-section flux number of your target atom, nuclear, whatever it is, okay? Why? Because when you're making, trying to measure, to weight the dynamical part of this, of your system, the phase between each of the atoms are uncorrelated, okay? So the idea that we exploit, also we measure, that it is possible to put in phase all the atoms in phase and frequency in such a way they are just all together answering this this signals that you're going to plug into this atom. Yes. How to do this? You have to build up a macro coherent state, okay? So instead of leaving your atom doing whatever they like to do, you have to try to build up a coherent state between a large amount of atoms. It is possible, yes, it is possible. How it is possible? Just using a laser, okay? If you use a pulse laser, and you know quite well how the response system of your atom or device, you can put we succeed to put for a small fraction of time something like 10 to the 14, 10 to the 15 atom all in phase altogether. Means that if I have, you see, going back to what I was saying, the dynamic going to the square, now I put n atom equal 10 to the 15 in phase each other. That means that they are going to respond to the external perturbation with the n square, not anymore with n. That means I will going to boost my detectability approach, you see, a lot. So I think that this will be the next step. So I think that if we want to go trying to be sensitive to this to the phenomena like relic neutrino, our dream, that we have our weak, very weak, much lower than weak section, I think we have to go this way. It's hard, it will take time. People already start to work on this, and I think also keep in mind for your future.
I think we can thank you.
Okay.
To say that I'm very happy of this talk. It was the first time that we have had this idea of this review talk on actions, phenomenology, and detectors. Exactly with this idea. So you see, we are quite schematic. Lipid nobles, boring, liquid scintillator, and water Cherenkov, crystals, and so on. But really, here we have some ideas out of the box. And to me, this is very important, both on the phenomenological approach and the experimental one. So let's see if there is any question, and then again, don't worry, it's not taking time from your coffee break. You will have half an hour coffee break, but let's see if there is any question.
I hope you have many questions.
Right.
I can talk now.
Okay.
Okay, I was just wondering, for liquid detectors, a lot of collaborations join to achieve, to achieve more. And I was wondering, because there are so many Axion experiments, so many small ones, we use similar technologies, but it would make sense, maybe like money-wise, so you can get, you have more. Would it make sense for joining?
I got to your point. Gianni, I think you see, you know that we have in nature boson and fermion, okay? And also this nature belongs also to the human approach. Means a large collaboration, you have to go through boson approach, you see? Small collaboration means you have fermion type of approach, you see? Just to say that the people are trying. I think what is good in this type of approach, that really small scale group, you see this typically American MIT, small group can push and get a good idea to get to say something on this Axion physics, okay? That is something that also the Americans are trying to do, you see, trying to put together these IBMX people in many universities, but I think it's not working. This is my point. So this is, I think, is a scale of physics really do not require this huge amount of people or group. Yale, you see, I think there are something like 10, 15 probably, overall 10, 15 people. Also IBMX at the same scale. Korea was quite large, now they are in the next year, they are just reducing the number of people just because they are just to converge to cover some of these regional microwave regions. So they just the funding agencies say, okay, now you show that you are good. Now you have to moving and scanning to a certain region. So it's like that. It's for the moment it's probably an experiment like Mad Max that we like to do in Germany. This probably you need a larger collaboration because it's a huge device. So I don't know if I just say give you a taste of what is happening with this group. I don't know if I satisfy.
Yeah, I just was wondering because like you mentioned the electricity part of like the magnet and everything, and I'm thinking like the big magnet is expensive, but if you have like a lot of people.
Yeah, I usually prefer to have smart idea, more to go instead of having large power consumption.
So let's see if there is another last question, and then other questions can be informally during the coffee break.
So I was not clear enough. Is that no question?
Or fully clear?
No. Fully clear, no. Not at all. I don't want to be fully clear. I want to suggest something. Yes. Wait, because this is probably is. I found this very okay. Please go to archive. Okay, this is a theoretician. This is an actual very nice one. Really, usually I keep exciting. Usually this is quite, you see, Axion for amateur. Okay, so it's not too difficult. And this is that they spread around the knowledge. They start from Newton, Maxwell, and move on. So I really suggest to go through this paper. I really suggest it.
Okay, so with this suggestion, we thank again. So, with the coffee break, first of all, the picture again in the small theater over there. We reconvene at 25 past 11 here on the statistical side.
Spero di non aver fatto troppo oscuro. Se fai queste robe così poi a tirare qualche tecnici.
Di oggi si parla di assuntorietà, sì,
No. Sorry, I don't know if I just answered to your question.
Oh, no.
The problem you see that is definitely that